This is lesson number 3 of the MII core. In this tutorial, we'll be talking about the output control of the MII model. So the code for this lesson can be found on the website projectfpga.com/tcp. So I'll be demonstrating this model, the output control model of the MII interface on Logisim. So the MII model performs 3 basic operations. 1. Writing control data to other devices, reading control data from other devices, and continuously scanning control data from other devices. So in this tutorial, we'll be seeing how is able to write his own control data to other devices. We by the name is output control. So this is how he's able to write his own output. So when he's reading, he's receiving bits of data called MDI, and while he's writing, sending bits of data called MDO. So this is the data here, MDO. So the MDO will be using this clock, the clock we generated in the previous tutorial. While this, from the output control, we found out that this is the clock we'll be using here. We have this here. FPGA is the control data that is being received. So in this output control, we found out that every flip-flop here, all the flip-flop here, only allows data when this is on. You can see every flip-flop here is only set when this is on. That is only on the rising edge of the MDO clock that you receive, that is able to send out outputs, and the MDI will be clocked using the other clock. So to be able to send this control data out, it uses 2 signals: the data itself, which is the MDO, and the enable signal. So this enable signal only comes on when this clock is on. We'll be able to set it. So we have this input here called the bit counter. What this bit counter essentially does is it counts the number of bits that have been sent out. It counts them: 1 bit, 2 bits, 3 bits, 4 bits. It keeps track of how many bits that have either been sent or has either been received. Then we have this another input here, no pre. This no pre means no preamble. So at the beginning of every transmission, a preamble is usually set. To know what a preamble means, you can go back to the site. At the introduction, I gave the different parts of the Ethernet frame, which usually starts with this preamble. This is the preamble here. It serves as So this in progress comes on whenever we are having either a read operation, a write operation, or a scan operation. So let's look carefully. Let me explain what is going on at this particular area. So let's look, so I will just demonstrate what exactly is happening at this particular area. This particular area, so in a situation whereby no control data is being transmitted, this MDOEN here is 0. That is, the output here is 0, and at that point the MDO is continuously outputting 1. And when will it output 1? That is when this data here, this signal is 1. It neglects anything here. This shifted bit is the control data that is being sent out. We'll still talk about how it's being generated in the other module. You see how this shifted bit is being generated. But mind you that is this MDCN, this clock that we generated from this here, this clock here, is what controls this output here. It turns on this multiplexer and determines when to enable, when this enable is going to work or not. So this MDCN is for MDO, the output, while the other one is for the input, MDI. But the two are being combined together and named MDIO. But the separation comes with this clock. When one receives at one edge, the other receives at another edge of the clock. So this shifted bit is the data that is being sent out. So if for any chance this is 1, the output of this is 1, the shifted bit will be negligent because this is a OR gate and everything will be all 1s. So if there is a 1 here, it means that no data is being transmitted. So the MDO is steadily high, is continuously high when there is no transmission, and this MDO, the enable bit, is 0. So let's see how these bits are being generated from this circuitry, because this is where they all originate from. So first, this AND gate here says when the counter is at 0, 0, that is initially beginning of the counter, and there is no preamble, then this here comes on. Here comes on. Or this OR gate now says, let's see what's in this OR gate. This OR gate means when there is a preamble and the counter is greater than 1F. 1F means 32. This is 1F. In decimal means 32. That is, the preamble is a 32-bit preamble. The preamble is made of 32-bit preamble. So it's now saying when there is no preamble and the counter is at 0, 0, or when there is a preamble and is at 32, the counter is already at 32. That is, they're actually neglecting the preamble. That is, after the preamble transmission, that is when you get the data transmission. And this AND gate here says when there is a write operation, this AND gate comes on. That is, write operation, the AND gate turns on. Or if there's a read operation, this is off. And when it's off, this particular one here is on. This AND gate down here, this one will be on. That is, this AND gate means a read operation, while this AND gate up here means for a write operation. So this is saying for either a write or a read operation. Then what again do we have here? This in progress, I told you, comes on whenever there is either a write operation, a read operation, or a scan operation. That is when this in progress turns on. That's what is essentially saying is doing a read operation or a write operation, and then this in progress is on, and let's see what's involved here. Here means when there is no preamble and the bit counter is already in 32, that is start of the data transmission, or when is at 32 and or when is greater than 32, that is after the preamble transmission and is less than 2e. 2e in hexadecimal means 46. After 32 is 16 bits from 32, that is after 16 bit data transmission. For this should be the read operation, that is after reading the 16 bit data or doing the write operation after the preamble, start of the data transmission, this comes on. Do you understand this? So this indicates, at this point it indicates that there is either a read or a write operation. So now this NOT gate, after this NOT gate means if there is no read or a write operation, that is when this particular point comes on. And likewise here it says when the bit counter, let's see what happens, is less than 20 in hexadecimal. 20 in hexadecimal. In decimal it means 32. If it's still less than 32, that is when there is no transmission and the counter is below 32, this comes on. And when it comes on and this enable is on, it goes in and comes here. And when it's here at this OR gate, it is going to make this OR gate to be called steadily 1, neglecting this shifted bit. That is, the outputs here at the MDO will be all 1. So what he's saying is, when it's not reading or writing, the MDO should be 1. So that is what he's saying. Because this NOT gate inverts this output here. But at this point, he's saying doing a read operation or a write operation. This means that the enable bit should be on. Doing a read or a write operation, the enable bit should be on. But here it's saying if it's not reading and if it's not writing, it should be off. It should produce a 1, and that 1 is going to make all the outputs of this MDO to be steadily 1. But if it's 0, that is when this shifted bit is the control bit of this ETMA core. The shifted bit, I'm going to show you where it's being generated. This shifted bit should be sent out of this MDO. So that is what is basically happening at this point, at this part of this circuit. This is how the MDO is being sent out. It means when it's not reading or writing, it should send out 1. If it's reading or writing, it should turn on this enable bit and it should be sending out what is being in this shifted bit. Because when it's on, here is 0, here will be 0. Because if here is 1, here is going to be 0, and here will now be 0, and then the shifted bit will be allowed to pass into the MDO. So the reason for this 3-stage memory D flip-flop is for synchronization. It doesn't just go in and come out immediately. It takes cycles for it to start, for the enable bit to come out. You are going to see these multiple stage settings a lot of places throughout this tutorial. They are just basically used for synchronization. They're basically used for synchronization. Then you will also see how we generate this bit counter. This bit counter continuously counts. It reads the number of bits for every pulse. It reads bits. And also be mindful of this clock. This is very, very important. This clock in here distinguishes between MDO, which is the sending out data, and the MDI, which is the receiving input data. The verilog code for this is here, is written here. The output controller, everything is likewise here. You see everything here. So I hope you understand. You can leave your questions on the website page of this particular tutorial. So let me elaborate more on this particular AND gate, what it does. This AND gate